Big time. So I'm going to do double duty here, but if it works, I can just start the meet at the beginning of the day and just leave it on. And then I don't have to worry about any recordings. But I can record my meets, and hopefully I'll just record them. And as long as I start and stop, I can start a new recording. So it should make it easy and keep me from having to do this, unless there's like a network issue, in which case they're out of luck. But hopefully, I'm doing a trial run today because a couple of guys have wanted to be in here live. So they can yell and ask me a question, which I don't know if they will, but if they could. But I have to actually record the whole screen.
You get like multiple cameras set up and like have different angles in the video.
Like ESPN, man. I get some 3D going on. Throw stuff at the camera. So today is the trial run. That I would like to do actually, because I think that would kind of give them more like they're there, but I'm legally not allowed to save those videos longer than 10 days. Like if I record a kid in a Google Meet, like if a kid is testing at home and I record him taking the test, they have to be gone and erased from the network after 10 days. So that's the rule they just handed down to us. I literally just got an email about it. So I can preview it for 10 days and check them for peeking at their phone or whatever. So if I video you guys, now granted, I guess I could go get 120 authorizations that I have permission to keep videos forever, but most parents don't want that, Why incriminate unnecessarily your children or put them in a position where, hey, he got a video of Johnny picking his nose and put it out there on the internet and profited off it. I don't think they want any of that. So until you are legal adults, which I doubt any of you will be in high school. In this state, it's 19. A couple of y'all? I will. You will be? So you turn 16 in ninth grade?
Yes.
Sweet. Were you driving in ninth grade?
No, I didn't have my license.
Oh, okay. Yeah, that's cool. Where I went to school, ninth grade was junior high. So if you turn 16 in junior high and you were pulling your car up or your truck or whatever in the parking lot, you were like a god, Really were. It's like, oh my gosh, Billy has a vehicle. It didn't matter how crappy it was, you were awesome, All right, guys, so today is determinant day. Everything there is determinants. We're going to be talking about the upside for you is you already know all of this. Well, you already have been taught all of this, so hopefully it will be a review. You can fill in the blanks because I realized you especially things like tricks that we've gone through. It's very easy to forget those. So we're going to run through those as quickly as possible. And then keep in mind, even if we're just plowing through this stuff, we're going to play the matrix game on Monday, right? And then on Tuesday, you guys have late arrival. So you won't be in this class, but you will be here that day, I'm assuming. So our test is bumped to Wednesday, and you can always come in here after school on Tuesday and get some help or whatever. Or if you don't have you can't come into this class anymore like that. But anyway, remember that too. So this is the last day of new material, but we can always fill in any blanks we need on Monday and Tuesday should you need that help. Okay, so jump with me to, where is it? Page 33, maybe. Might be a little different. It's different.
Is it day 4, 5, 5?
Yes. Yes. So jump with me to page 35. And let us see what we can do. So we've already talked about the diagonal method, right? And I kind of use the diagonal method for 2x2s to evaluate a determinant. I'm not doing expansion by minors on this, right? Just that times that minus that times that, we're done. 3x3s, I gotta be honest with you, I don't even use the diagonal method anymore. I don't. I think it was one of those things that Algebra 2 teachers made up because it doesn't work with anything but these two. It's just a coincidence. but I think Algebra 2 teachers made it up because the whole idea of expansion by minors bothered weaker students. And this kind of made more sense to them. Oh yeah, multiply those diagonals, multiply these. But if you want to do the diagonal method, knock yourself out. Remember, you just copy down the first 2 columns there. Actually, I even taught you a different way. But the official way is to copy down the first 2 columns and then multiply the numbers in the diagonals going down, and then add those 3 up, and then multiply the numbers in the diagonals going up, and subtract those 3 amounts. And then when you get your final result, that's the determinant. I think I told you a little bit differently. I said, go that times that times that, and then go that times that times that, and then go that times that, going down, add those results. And then when you're done with this times this times this, subtract that, this times this times that, subtract that, and then finally this times this times this, and subtract that. I think I used the analogy of the game of like asteroids or Pac-Man back in the day. Like if you fly out, I talked about like if you're playing, have anyone ever played asteroids? It's an old 1980s Atari game, and you have this little bitty thing like this, and literally your sole objective is to shoot a rock and not be shot by the little spaceship that goes by. That's it. I played that thing for hours. I mean, it was awesome. And you guys are like, that's the most boring game ever. But my son actually bought me the old, you can buy like a little console, and the joystick is literally a stick with a red button. And it has a ton of old Atari games on it, and it's like brought me home, you know. But anyway, I have that little thing. But anyway, if you're flying on this little ship and you go out one side, if you go into the end of the screen, you come out the other side like that. And that's kind of the idea here. As you're multiplying, if you don't hit 3 numbers and you just hit 2 or just 1, then come out the other side and pick up the other 2. So that was kind of my explanation of how you navigated that. But anyway, I think it's obsolete and kind of crap. If you like it, there's no shame in that. I mean, use it away. Be great. Just remember, these numbers are the ones you add, and those are the ones you subtract. Same thing when you're doing it up here. That's the one that you don't change the sign. That's the one you do. But I'm a bigger fan of expansion by minors, and that's what I use all the time, mainly because it requires less writing for me. Like, you know, like if I know I say use the diagonal method or whatever, do it as much as you want. But I like expanding by minors because I don't have to write much. You know, like for me, I can just say, okay, I typically pick the first row unless I see an abundance of zeros somewhere, and then maybe I'll pick a different row or a different column. But I say, okay, if I pick the 0, the 2, and the 3, and then put parentheses for the minor, then I remember the plus, minus, plus stuff. If I pick the first row, save it, change it, save it. So don't change the sign, change the sign, don't change the sign. And then all I have to do now is take the minor of each of those numbers, which we were doing yesterday when we did inverses, right? What's the minor of the 0? -2 minus nothing. Put it there. What's the minor of the 2? Are y'all able to see it? +2 minus that 12. Put it there. And the minor of the 3, nothing minus that -3, +3. So when I do this, all I see is this. And that's all I would really expect you to see. Now, if you want to write the actual determinant out there, like if you want to say 0 times its minor, not that you would do that with the 0, but if you want to write the minor, that's great. But again, what I just write is what's needed, which is the actual value of the determinant of the minor. So anyway, that goes away and you get 20 plus 9. So that's how I'm going to evaluate determinants, almost, maybe not on my keys because some of my keys are older and I was a little bit more diverse back then. I did some with diagonal, some with expansion by minors, but this is what I do now. If I ask you to do it by a certain row or a certain column, I want you to do that so it makes me easier to grade, and so that I can check to see that you know what to do with the minuses and the positives. So like if I said second column, and you're saying 2 times the minor, 3 times the minor, 0 times the minor, what do you do with the signs of the 2 and the 3 here? You're going to negate the 2 don't negate the 3, right? Because remember, it goes like, this would be a plus that I'm pointing at, minus plus, minus plus, minus, plus, minus, plus. So I would have negated the 2 and the 0, not that I need to do anything with that 0, and then I would not have done anything to that number. So when you have those negative spots, it doesn't mean make it negative, although that's what's been happening here. And when you have a positive, it doesn't mean make it positive. It just means if it's in a negative spot, change the sign. And the minor of the 2, 4 plus 10, and the minor of the 3, 3 minus 2. And you don't have to bother with the minor of the 0. So again, you do whatever you want on these 3x3s unless it specifies what to do. But if it does specify it, make sure you're at least showing me this, right? And you will have a calculator for a couple of the problems because I want to make sure you can do like reduced or echelon form and yada, yada, yada. But probably only like 3, and the rest will be manual stuff. All right? So problem like this next one where I give you a 4x4, I would not give you anything bigger than a 3x3 unless there was an easy way out. So right here it says evaluate by the third column, right? So there's your third column. Obviously, that's a great choice, right? Makes your life pretty easy. So 5 times its minor. So what is the minor of that 5? Now that I can't do in my head, so I'm going to write it down. What would be the minor of that 5? Getting rid of everything in the row and column. 0, -1, -1, -1, 1, 3, 0, 3, 3. What would you do now? Now you could do the diagonal method now if you want, but I see a column with a bunch of zeros. I also see something else I'll talk about in a second, but I see a column with a bunch of zeros. So I'm going to go 5 times, and I'm going to expand by that column, which means all I have to do is multiply by the -1 times its minor. But is the -1 now in a negative spot? Yeah, plus, minus, plus. It's a negative, so I'm going to change the sign of the -1. And then I'm going to take the minor of the -1, which is -3 minus a -3. Oh, how convenient. But this leads us to a rule we'll talk about today. We said we are allowed on any determinant, if we want, we can multiply a row by something as long as we multiply the outside by the reciprocal. We're going to talk about this in a second. So even though this one was 0, we're happy it didn't take too long to get there. If I look back up here, I could multiply that row by 3 as long as I multiply the outside by the reciprocal. It kind of balances it. It's like if I had $10, I can multiply by 2, as long as that makes it not $10 anymore. But if I also multiply by a half, it's back to $10. So I did 2 things that balance each other out. Now, you also have a rule in matrices that if 2 rows are together, which I can make them together by switching, although we're going to talk about that in a second. If I switch 2 rows, I would have to take a negative out. But if I ever look at this and I see any 2 rows that are the same or opposites, any 2, I'm going to end up getting a 0. So just looking at this, I go, well, those are opposites. So when I evaluate this, I'm going to end up getting a 0. But it didn't take too long just to expand using expansion of my minors. Are you with me? A couple other little things that I might throw at you. These are kind of math team level things. Little ciphering questions you might see, like 6 and 7. But if you see something that says solve for x, I have a determinant equal to 3 and a determinant equal to 20. So you're solving for the variable that would make that happen. Any ideas? So just evaluate it. So you'd say that times that, which is what? Negative, I'm going to write it out actually. 5 plus 2x times -6 minus 3 times x minus 1. And all of that would have to equal 3. And then you just got an algebra problem. And on this one, you're only going to have 1 x. But what if the x's were right here where I'm pointing? If the x's were right here, then you're going to end up with an x squared, wouldn't you? So if I end up with an x squared, you're probably going to have something that you have to factor or use a quadratic formula for. Don't be afraid of that. It might not be something you're used to seeing, but that's totally something that can happen. I'm not going to finish that unless you need me to. Do you need me to? And then same thing here. If I start evaluating this, doing the diagonal method or expansion by minors, or whatever you want to do, I like expansion by minors. In fact, not only do I like expansion by minors, I like to pick the x value to be in the row or the column. And you don't have to, it doesn't matter. It'll work out either way, but I just kind of like that because it puts the x on the outside. Right, that's your call. So hypothetically, say I were to expand by this, 3 times its minor, change this positive, negative, positive, negative, positive. So change the sign of the x times its minor plus the 6 times its minor has to equal 20. So what's the minor of the 3? So everybody with me? So 12 plus 5 is 17. And the minor of the x, 5, good. And the minor of the 6, 14. And you can see right here, that ends up not being a very difficult algebra problem. So just be careful. Show me at least that much work. And I realize my work may be different than yours when you pick a different row, or if you do the diagonal method. If you do the diagonal method, you're going to end up having 2 x's. One from when the diagonal comes down, one from when it goes up. That's okay. Just add the x's together. So you should be fine on any of these, I think. If you're not, just see me, send me an email, text, something. All right, before we get into all the ugly little rules, I want to remind you about Cramer's rule. Do y'all remember Cramer's rule? It's in the determinant section because remember, unlike reduced row echelon form or unlike inverses that use matrices, Cramer's rule uses determinants only. And it's a little trick. It's obsolete, not obsolete so much, but I don't ever use it when I solve. I rarely, if ever, do I ever use it when I solve. But it does rear its head every now and then. I seriously doubt that I'm going to give you something like this and say, solve using Cramer's rule, because that requires you to do 4 3x3 determinants. But what I a lot of times do will say, hey, what would you set up what you would do to find x? And don't bother simplifying. Just set it up using Cramer's rule. So we learned in Cramer's rule, you needed to find 4 determinants. We called them the d determinant. We call them the dx, d sub x, d sub y, d sub z. And you had one d for every variable, and then you had d for what we call the coefficient matrix. So if I only wanted to find x, and then when we were done with these, the way I found x is I would say x is the dx over the d, and then y would be the dy over the d, and z would be the dz over the d. But if I only want to find x, I only have to find those 2 determinants. You tracking with me? So if all I need is x, then I just need d and dx. Well, d, when you look at it, it's just the coefficient matrix. So take the coefficients, stick them in a determinant, do the evaluation. And again, these are old keys, and sometimes that's the diagonal method. I don't really use that anymore. So if it were me, you'd probably, if I was doing it now, I'd probably go 3, minor, change the sign, minor, 1, minor, and then I'd go minor, 4, minus 4, that's nice, negative 2, minus 20, not as nice, and then 1, plus 10, and I would get that negative 88 plus 11 is negative 77. So I personally like it. I think it's quicker than doing all the multiplication on the diagonals, but that's completely your call. Okay? So once I get D, I've got the first part. So if I'm looking for X now, the D part goes on the bottom, I've got it. Negative 77 would go down there. But now I need the DX. So the DX literally is the D, and then you just go in there and you get rid of this part and replace it with what? That. And the reason why you replace that column and not the other ones is the X's were in that column. Kind of seems like, I remember kind of thinking back in the day, it seems like you should keep the X's because it's the DX. But no, you get rid of the X's and replace that there. And the why behind it, guys, is, again, these are tricks. Determinants, matrices, they're a way to organize information in a kind of a tricky way that alleviates the actual thinking of the substitution, the elimination. Somebody noticed those patterns. They noticed they worked. They said, here, you can use these. So really, all of these are kind of tricks that help you out here. If you plug those in there and simplify again, you get the negative 154. So at this point, I know my dx and my d, and you could just plug your negative 154 over your negative 77, and you're good. But what you would have had to do is just write this down, take the dx, put it over the d, right here, take that, put it down here, and that would be your x. You've answered the question. If I were to say, set it up without simplifying. And that's probably what I'll do, because I want to see that you know it, but I don't need to make your life miserable by asking you to evaluate a couple more determinants. It's just time consuming, and I want you to be able to focus on a bunch of different problems. Are y'all with me?
Does the book do it like it do?
For
Because I was
Kramer's rule?
Well, I was looking at the homework and like the solutions last night, and it was like it had the answers in another matrix, and then it had like X, Y, Z is in another matrix, and it was next to it.
In the book?
Yeah.
Was it Kramer's rule?
No, it wasn't Kramer's rule.
Oh,
but it was
well,
like,
yeah, there's a zillion different ways you can solve.
okay.
Yeah, like if I was solving this, I would have put it in, like if you told me solve as fast as you can, I'm going to put this in an augmented matrix, and I'm going to RREF it. You know what I'm saying? I'm going to put 3, negative 4, 1, 14, 1, negative 2, 4, 20. It's just quicker. This is dumb, okay? But keep in mind that 20, 30 years ago, not everybody had a calculator that did this. So then I'm like, well, actually, it's probably a little quicker for me to find X, finding a couple, because I can do a 3x3 determinant. You've seen it, and you can too, pretty quickly, right? I can do a couple of those pretty quickly and get X. Whereas solving this using actual Gaussian elimination and back substitution like you did on your past test, that's pretty time consuming, right? And keep in mind, if your goal is just to solve it, as soon as I get X, what could I do with that X if I had to do this manually? I could get X with Kramer's rule, and you found that X was 2, right? Couldn't you do this at this point? Now that you know X is 2, couldn't you go, all right, I'm just going to plug 2 into a couple of these, and I'm going to take these, negative 4y plus z, and I'm going to take this 6 and subtract it. And then I'm going to take that 2, and I'm going to subtract it. And now I could just use that, solve for y and z, right? So I could use Kramer's rule to help me out real quickly, and then I could just solve a simple system. I could multiply the bottom by a negative 2, boom, I've got my z, plug it back in, I got my y, I'm done. And I did actually use Kramer's rule. But I'm not going to make you go through the whole process. You're going to do a setup to show me that you know how to do it, and then we're going to move on. Because again, I'm kind of tied, my hands are tied a little bit on what I do in pre-cal. There's like a course of study out there, a national one and a state one, and it has all these topics you have to cover. So it wants me to cover this, but it doesn't need me to make you masters of whatever and use it all the time when there are better ways to do it. So I'm holding a calculator, I'm doing RREF. If I am not holding a calculator, I'm doing this. Honestly, I don't know that I would do this. I just don't know. It just seems like a lot of math to do just to find a single variable when there's other ways to go about this. Okay. Anybody got any questions on Kramer's rule? I know that last year I tested you on a bunch of things like what happens if the D is 0? You know, and we said, oh, that means no solution. Well, sometimes it means no solution. Sometimes it means infinitely many solutions. And infinitely many solutions, these are planes. So infinitely many could mean like they cross on a line. So we're not going to get into all that on this test. That was more of an algebra 2 thing. And then, so anyway, this is all you would have to do on yours. I'm not going to make you do all 3 of these, but again, just to point out, if I was looking for dy, replace the y's, dz, replace the z's. So, but I'm not going to get into that. I'll probably ask you one variable. Show me the setup. Don't bother simplifying. I'll make that clear in the instructions as well. So, so solving the system, I'll leave that to you. I don't want to spend a whole lot more time on this. All right, so let me talk about the properties of determinants. Okay, the first one I want to talk about, do you remember the one where you have the diagonals going on? And then you have either all zeros above the diagonal or all zeros below the diagonal, right? Or maybe both. Well, I can get you to memorize the rules, and I'll mention them quickly, and then I'm going to very shortly kind of just show you the why, okay? Because some people like the why. I know I like the why. it helps bail me out when I can't think. Although it's a lot easier to remember just the how. So if ever the diagonal comes down, right, from top left to bottom right, and you can see I put zeros above on all of these. All above the diagonal, you can see zeros. And I mean completely zeros, right? So if it's completely above or completely below or both, then the rule is all you have to do is multiply the numbers that are in the diagonal, and that is the result of your determinant. It does not matter what the other numbers are. And again, that's if the diagonal's going down to the right. Can anybody tell me the reason?
Diagonal method, but then.
Well, the diagonal method doesn't work on these, so give me something that works on all of them. Because remember, diagonal method is a trick that only works on 2x2s and 3x3s. Make sure you remember that. I remember when the internet first came out, like literally. I remember them sending out a memo. I don't know how, an announcement on the speaker because we didn't have email. And they're like, hey, if anybody wants to play with the internet. We were like, the internet? What is the internet? If anybody wants to play with it, come to room so-and-so and you can spend an hour playing with it. So I remember me and, anybody have Mr. Health? Mr. Health's dad was here. And me and Mr. Health went down there and we were playing with the internet. And I remember I was going skiing, or was planning it, and it got canceled, but I was going to go skiing up in British Columbia, this place called Whistler in Blackcomb. And I was like, man, maybe there's a trail map I could download. So I found their website, which, you know, it took, this is dial-up. Do y'all let me know what dial-up is? Okay. Anyway, it was like dial-up internet. So it was like, I made all these funny noises. It was just trying to connect. And it took like minutes. But when I finally got up there, and so I got in their website and I found the trail map and I clicked the download. And it was like one little pixel line at a time coming in. And I was like, well, this is going to take a while. So we went to lunch. Came back from lunch, like an hour and 50 minutes later. This is like a teacher workday. Came back and it was like half there. It was that slow. It was just incredibly awful. And there's a reason why I was telling you this.
Yeah. Where we were going with it.
It was a good story.
That was a good story. Walk down memory lane. That's what happens when you start getting older. All right, maybe it'll come back to me, but man. Whatever. Jumping back to this, guys. That is weird. Jumping back to this. If I cannot. I know why. So I also remember you find these people's math websites, and there was just like, but that was back before everybody had internet, and you couldn't get on there. It was back before they had like comments that you could put at the bottom, like, you stupid idiots, you don't know determinants, quit posting bad math. But you would see things like the diagonal method working. They would show examples. The diagonal method works for all matrices. I'm like, dude, it does not. But people didn't know, and they would put out crap information, which they still do. I mean, it's filled with crap. But at least you have enough people commenting at the bottom like, you loser, learn your math. Back then it was like free reign with no accountability. It felt that way. But anyway, on these, I would have to expand by minors, wouldn't I? Because that's the only way you can do that. But check out expansion by minors. What would you pick, for example? So if you pick that, because why not? It's got a bunch of zeros. Your other option maybe be this one. But if I did, I would say 2 times its minor. Now, 2's minor is this thing, right? Okay, so what's the minor? I mean, what's the determinant there? How would you do it? Oh, I would probably pick that row. So I would go -4 times its minor. And its minor is that thing. And then how would you do that thing? Oh, well, 7 times 5, because that goes away. So what do I end up with? 2 times -4 times 7 times 5. Right? So that works anytime you have zeros above or zeros below. Anytime. So why not take advantage of it? So if it's going down like that, just multiply the numbers together. Yeah, and it's possible it ends up being negative, but you don't change the sign. Okay? And that's true on every size. But that's not true when the diagonal comes up. And the reason why is, you'll notice every time I pick a minor here, I'm always picking the top left corner of the minor when I expand, aren't I? I pick the 3, which is in a positive spot. I pick the 4, which is now in a positive spot. right? And if I'm always picking numbers in positive spots, nothing changes. But check out these when it goes up. Right here. Here, I think I told you this last year, but I taught this wrong for years. I feel terrible. I was trying to notice patterns, and I checked out the patterns coming down. I'm like, oh, it never changes the sign. And then I checked this one, and I'm like, oh, this changes the sign. So I checked one here, oh, change the sign. I'm like, oh, change the sign when it goes up. And we went to a tournament in like Huntsville or something, and some kid came back and goes, your rule doesn't work. I'm like, yes, it does. No, it doesn't, mister. I thought I was right. I missed it. I said, look, and I typed it in my calculator. And it didn't work. So what I noticed was I quit too early on my check, and I really didn't think about the process. But right here, notice this. It's clearly 2 times that's nothing. And then we know that you go nothing minus that times that. So when you look at this one, it looks like I negated the diagonal. Now, if I was expanding here, and again, notice I'm going up with my diagonal. If you were to pick a row or column, isn't this a likely row or column that you would pick? So you would say 1 times its minor, right? And the minor would be that. And you already just learned that on 2x2s, what do you do? You negate the diagonal. Not that you would have to memorize that, but look, you go nothing minus the -4 times the 7. Well, what's the net result of this? You've got a negative 1 times -4 times 7. So it looks really clearly right now like I'm just negating the diagonal. And that's where I quit checking and just assumed. But look, this, check it out. So again, 2x2, negate the diagonal. 3x3s, negate the diagonal. Right? 4x4, 1 times its minor, right? And the minor is a 3x3, isn't it? But check out 1. What space is 1 in? Plus, minus, plus, minus. So on this one, I'm going negative that number times a 3x3. But the rule for a 3x3 is what? 3x3s, I negate the diagonal. So without showing you the work over and over again, I end up going negative times 1 times negative times that's the minor, times the diagonal. So the -4, the 7, and the 3, what do these two negatives end up doing? Cancel each other, and what am I left with? Just the diagonal. So on a 4x4, I don't negate it. So at this point, I was like, okay. So I told my kids wrong for 3 or 4 years. It finally caught up with us, and we missed one. We missed 4 times, cost us 16 points at a math tournament. No, it cost us 20 because they missed it, so they got a -1. But right here, I started noticing, and I went and checked the 5x5 and the 6x6, and then I realized what I was actually doing made sense. But there was a pattern to it, and the pattern was on the 2x2s and the 3x3s, like we just saw, on 2x2s and 3x3s, multiply the elements times a -1 in the diagonal. So negate the diagonal. But on a 4x4 or 5x5, then you don't negate it. And it alternates like that every 2. Guess what the biggest mistake is people make? Even if they got the rule, they kind of understand that the alternate, they do this. 1x1s and 2x2s, negate the diagonal. Now, first of all, that's a 1x1. Man, how do I evaluate that? What to do? There's nothing to do, right? On a 1x1, so we don't even talk about 1x1s. So start your rule with the 2x2. 2 and 3, negate the diagonal. 4 and 5, don't. 6 and 7, negate. 8 and 9, don't, etc., etc. And I'll probably give you some big 11x11 and see if you know your rules, or 15x15. So make sure you count the rows and the columns. And then if you're like, are you really going to make me multiply 11 numbers together? Yes, probably will. But I put a lot of 2s and 5s in there that make 10s. I put a lot of 1s and negative 1s that don't do much. So it's never anything that's going to be overly terrible, but I will do that. All right. So those are your diagonal rules. Those show up a good bit. Also, a couple other rules. Anytime you got a row filled with zeros, obviously, if you expand by that row, you get a 0, right? So obviously that's true. Probably not a really big math team question. Also, Gaussian elimination works with determinants. But here's the condition. It only works on rows that connect to each other. All right, so, but a lot of the rules you can use don't matter whether they connect or not. So right here, I want to give you an example. Look at these two rows. What do you notice about them? They're opposites. So they're right next to each other. What would happen if I added these? And by the way, Gaussian works, you can add any two rows together and replace one of the rows with the result. So if I add these together and replace one of the rows with the result, what do I get? A row of zeros. Do I expect you to do Gaussian? No. What I expect you to know is if you see opposite rows or opposite columns, either one, and actually they can actually be anywhere because switching two rows or switching two columns just negates it. So like if I take this second and third row and switch them, my answer becomes negated. But does it matter if I'm negating a negative? I mean, and a 0? No, it doesn't matter. So any two rows, any two columns, opposites, always 0. Now, what about if they're the same? If any two rows or any two columns are the same, like these two, they're also going to be 0 because you remember the rule I mentioned earlier? I said you have the right to multiply anything you want by a negative as long as you put a negative on the outside to balance it out. So if I negated this, then put a -1 on the outside, right? What do I have? Two opposites? And if I have two opposites, what would happen if I added them together? I would get a row of zeros. And if I get a row of zeros, the whole determinant is 0. So there's another rule. So if you get a row of zeros, it's 0. If you get two of the same rows or columns, it's 0. If you get two that are opposite, it's 0. All right. Another one that's built on this whole property, and I don't know if you remember these, but do you remember stuff like where you go +3, +3, +3, +3, +3, +3, where you're adding the same thing, +3, +3, +3. Now you might look at this bottom one and go, the bottom one's not doing that. Let me talk about that. And then coming down, +6, +6, +6, +6, +6, +6. As long as you have either 3 rows or 3 columns that are behaving this way, it doesn't matter about any of the other ones. It's always equal to 0. Why? What would happen, hypothetically, track with me, if I did this, inside and out negative, and then combined these 2 rows together? What would I get? 6, 6, 6, 6. Okay, so I'm going to replace this with 6s. Now, what would happen if I negated the second row and then put a negative out there to balance it and added these two together? 6, 6, 6, 6. And if I do that, what do I now have? Matching rows. Now, do I want to do all this every time? No. So I only needed 3 rows to do that. Can't do it with 2, have to do it with 3 because I have to change one of them and then change the other one. So if you see a pattern like that holding for either 3 rows or 3 columns, and it can be any number, whatever, that you're adding the same thing across, and in those 3, you have to be adding the same thing across right here, and then you have to be adding the same thing down. It doesn't have to be the same number here and here, but as long as I see that for any 3 rows or any 3 columns, I'm always going to get a 0. You can see it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I want an extra row, but it's not even important because it worked for those 3, right? If I see that, 0. You with me? This is did I give you the story about I'm feeling 4? That's what this was. This problem showed up, except it went 15, 6, all the way through 21, 22, 23, 25. We had talked about it so much. I mean, it showed up. Yes. And it dominated. I was feeling forward. Whatever. All right, here's the last part we're going to talk about. How much time we got? Might be all right. If not, we'll try to talk about it on Monday, but we'll see. Okay, so I've already mentioned a couple things like if you multiply something on the inside, you'd have to multiply something on the outside to balance it, right? And I also said if you, so the reciprocal on the outside, I said if you ever switch two rows, and by the way, they have to be two adjacent rows. I can't like switch row 1 and row 4. If I switch like row 1 and row 2, what happens to the value of the determinant? It gets negated. I'll show you a simple example. Look at this. 2, 3, 5, 1. 2 minus 15, negative 13. Look what happens if I switch these two rows. 15 minus 2. So just switching any two rows negates the value. But it has to be adjacent rows. So if I want to switch row 1 and row 3, I have to do it through a series of processes. Think about it. Like if I want to go from A, B, C, D, E, F, G, H, I to, if I want the D, E, F to be here and the G, H, I to be here and the A, B, C to be down below, I've got to do a couple switches. Like for instance, if I want A, B, C to get down to the bottom, I can't just put it down there and go, oh, that's a -1. I would have to switch these two. So here we go, D, E, F, A, B, C, and that's going to negate my answer by a negative. And then if I want to further move the A, B, C down, I would have to switch again. And that gives me A, B, C, G, H, I. And that would give me another negative. Now the net result is the two negatives cancel, right? So nothing really happened to change on this particular one, but your switches have to occur that way. Same thing with columns. You can switch any two adjacent columns, but every switch changes your value of the resulting determinant by a negative. Are you with me? Okay, so here's an example of maybe what you're given, and then I'm going to show you a trick that you can do these with, a logical trick. So example, whatever, I'm telling you that this matrix, XYZ, ABC, MNQ is equal to A. So if this is A, what is that equal to? So what I'm going to do is think about this equation and think, okay, I don't have just a single matrix, right? If I had a single determinant, I don't have that where if I want to multiply by a negative on the inside, I got to balance it with a negative on the outside, right? Or if I want to multiply by a 2 on the inside, I got to put a 1/2 on the outside. I've got an equation now. So I can just multiply both sides by a 2 or both sides by a 3. So looking at this, what happened to A, which is this, to give me this? Well, the first thing I'm looking at and I'm seeing is it looks like the ABC got moved up and the XYZ got moved down. Are y'all seeing that? So what would that have done? It would have negated it, right? So if I switch the XYZ down to here and the ABC to here, that would have negated this. Are you with me? Yes, no? I'm going to multiply both sides by a negative. Swing it over here to the A. Because I want my answer. I want to know what that is in terms of A. So like right now, this is -8. Now it looked like the M and Q stayed put. Now what else looked like happened to go from here to here? Say it again. Okay, it looked like somebody multiplied the XYZ by a 2, but I got an equation, so why don't I go, I'm just going to multiply both sides by a 2, and I'm going to multiply the 2 through there. So 2x, 2y, 2z. This is now equal to -2a. What else happened?
Third row by 6.
Third row by a 6. Now I know there's a negative up there, so that's something else that's going on. But third row by a 6. So that's the same thing as me multiplying both sides by a 6, which gives me -12, 6. But I'm going to choose to multiply the 6 into that column, and that gives me 6, 12, 6. Now, if you're asking this question,
I thought with a matrix, you multiplied the number into everything. That's a true statement, but this isn't a matrix. On a matrix, you do multiply it into everything. We did that yesterday. On a determinant, you can pick any row, any one row, or any one column. That's the rule in the determinant. And we normally don't want to do that. Who wants to multiply a number into a determinant that you now have to evaluate with bigger numbers? That doesn't make any sense. But in this case, they're forcing our hand. All right, what's the last thing? Multiply both sides by a negative. And I'm going to multiply the negative into the top row. So I'm pulling that in. And the two negatives give me a positive. So 12a equals this. So what is this in terms of a? 12a. Now, there is an easier way to go about doing this particular problem. A lot easier. And that is, according to this is a. So if I were to go about the business of doing, say, the diagonal method or expansion by minors or anything like that, I would get a big, long, ugly example of what that is, right? I would get something like xdq plus ycm plus zan, yada, 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 right? This is the one example I think it's helpful knowing the diagonal method. So right here, I know that a is equal to a whole bunch of things, right? But one of them is coming down this way, xbq. Well, which diagonal here has an x and a b and a q in it? There's the x, there's the b, there's the q. What would I have to do to hit all three of those in one swoop? I would have to be going up through that diagonal. Do y'all see that? But when you go up, do you add it or negate it? So this problem is equal to negative 6q, 2x, negative b, which is what? 12xbq. Now it's got a bunch of other junk going on too, right? Just like this one did. But look, what's the difference between these? 12? Well, if this is a, then what is this? 12a. So you can just use that to dictate what's going on. And that's all I got for today. All right, so that's everything new, guys. Do the best you can on everything I've given you. We'll see you on Monday, and have a great weekend.